Now we are discussing about light emitting diode. Usually we hear the word LED, that is very famous. LED bulbs in our homes we observe. We observe some LED displays in the railway stations. Behind the LCD display screen there is an LED to give the light, and sometimes in the functions we observe small LEDs. These LEDs which we observe in the different forms, whether the LEDs which we are observing in the small form for giving the blinking lighting, or the LEDs we are observing in our homes, or the LEDs we are observing which are giving the light to the LCD displays in the railway stations or in sweet shops. For all these LEDs, the basic concepts we have already discussed in the semiconductor physics, because LED means a light emitting diode. This is a PN junction diode which is having the capability to deliver the light, to emit the light. So this is a PN junction diode, but this PN junction diode is special because it is emitting the light. This PN junction diode we are not making by using a simple silicon or germanium. Sir, you have said already silicon is the famous semiconductor. We are using the silicon for the PN junction and we are using the silicon for the many semiconducting devices. Yes, that is absolutely correct. Because of its durability, because of its ability to withstand the temperature, because of its ability to withstand the electric current, we are using the silicon compared to germanium, even though we discussed about the group 4 semiconductors, silicon and germanium. We are using the silicon. But this silicon PN junction diode, it will not emit the light. We require the light. At that time, we have to use the compound semiconductor. Here you see, this is gallium and arsenide. This is group 3 and group 5 elements. Gallium arsenide is a semiconductor. So we are mixing two elements to make a compound semiconductor. So here we have different types of the semiconductors. Gallium nitrate, gallium arsenide, gallium phosphate, gallium arsenide phosphate, and aluminum gallium indium phosphate. When we take these particular compound semiconductors, when we make a PN junction diode by using these semiconductor devices, that PN junction diode is capable of emitting the light. Here we are seeing the physical view of the LED. That's what we observe in our laboratories also. This is a PN junction diode, which we have already discussed. There is a reflector. Generally we use either gold film or any other film which is capable of reflecting light, metallic film. So this is a reflector. We are using two metallic elements. This is anode and cathode like any other PN junction diode. We are connecting two metallic terminals. This is anode and cathode. For the LED, generally the anode will be longer pin compared to cathode, because we are giving only the DC supply. We have to differentiate between the terminals. If we make the same terminals, then we do not know what is anode and what is cathode, because LED should be always forward biased. We should never connect LED in the reverse bias. If we connect the LED in the reverse bias, it will automatically get damaged. So because we are connecting the LED in the forward biased, P-type semiconductor should be connected to the positive terminal of the battery, and the N-type semiconductor should be connected to the negative terminal of the battery. This is the depletion region. It is forward biased, and on the P side you can observe there are positively charged ions. These are immobile charge carriers. Here you can observe immobile negatively charged ions. This region we have called with the name, what is the name of that region? Depletion region. This is also called as space charged region, because in that region there are no free charge carriers. There are no moving charge carriers. Here we are observing only immobile charged ions. So this is nothing but an insulator. Or an insulator, we are calling this as a depletion region. An insulator we are calling as a space charged region. This insulator, here we have taken the PN junction diode. On the both sides will have the same width if we are using the doping on the both sides as same. Here we are taking the PN material, example we are taking either gallium nitrate or gallium arsenate. Then when it is forward biased, what are the majority charge carriers in the n-type semiconductor? Electrons are the majority charge carriers. What are the majority charge carriers in p-type semiconductor? Because it is forward biased from the n-type semiconductor to the p-type semiconductor, which charge carriers will move? Electrons. From p to n, holes. When the electrons are moving from n to p, because it is forward biased, for the LED, compare it to the normal semiconductor material we have discussed, silicon and germanium. Here the cut-in voltage is little bit more. It is 1.6 volts and 1.7 volts, 1.8 volts, depending on the color of the LED. Okay, the barrier potential we have given the supply more than the barrier potential. The LED is forward biased. Electrons are moving from the n-type semiconductor to the p-type semiconductor. Here this is a conduction band, this is a valence band. When electrons are moving from n-type semiconductor to the p-type semiconductor, the electrons in the interatomic gaps, they are recombining with the holes. So these electrons in the conduction band are recombining with the holes. When they are recombining with the holes, they are releasing the energy in the form of the light. This is how a light emitting diode is working. The principle is simple. We are connecting this PN junction diode in forward bias. We should never connect this PN junction diode in reverse bias. Because this is connected in the forward bias, the majority charge carriers are moving from N region to the P region. The majority charge carriers are electrons. When electrons are moving from N to P region, these electrons in the P region, they are trying to recombine with the holes. These electrons are free electrons, but now these electrons are going again into the covalent bonds. So again they are becoming bounded electrons. So these electrons in the conduction band, they are moving to the valence band by releasing the energy. This energy is nothing but the light. That is what we are seeing in our homes. Sir, what are the different types of the light we are observing? You can observe some red light. Then you are using gallium phosphate. If you are using gallium arsenate phosphate, then you can observe the yellow light. Different materials, based on the PN material we are using, the color of the light the LED is emitting is changing. When you are observing the white light, then the PN material you are using is a silicon carbide. These different lights, white light, red light, green light, yellow light, orange light, to emit these different lights, we have to use the different compound semiconductors, because these semiconductors have the property. When the electrons move from the conduction band to valence band, they release the energy in the form of the light. If you take the silicon, when the electrons are moving from the conduction band to valence band, they release the energy in the form of heat. But in the case of the gallium arsenate, or in the case of the gallium nitrate, or in the case of the gallium arsenate phosphate, the electrons, when they are moving from the conduction band to valence band, they are releasing energy in the form of the light. We have captured this principle, and based on the material, if we are using gallium arsenate, it is giving some light. This is called as infrared light. This light we cannot see with our eyes. This is the visible spectrum of the light. If we use any light below the red, then we are calling that as the infrared light. we use our TV remotes to operate with the infrared light. If we are using any light beyond the violet, then we are calling that as the ultraviolet. We cannot see the ultraviolet, and either we cannot see the infrared. Because we are not able to see that light, because there is no color to that light, we are calling that as infrared. That is below the red. Ultraviolet, because that is above the violet. Ultraviolet rays we are receiving from the sun. That is how our ozone layer is working to protect us from the sun. And infrared rays we are using with our TV remote. So we are familiar with these two, ultraviolet and infrared rays. To generate the ultraviolet light, we use the gallium nitride. We cannot see with our eyes. To generate the infrared light, we use the gallium arsenide. We cannot see with our eyes. But these colors we can see with our eyes. So infrared LEDs can be used in your CCTV cameras. Infrared LEDs also, they are emitting the light, but you cannot see that light. If the light is red color, you can see some red color light is coming. If that light is yellow color, you can see some yellow color light is coming. How the light is coming? The principle is same. We are connecting the LED in the forward bias. This positive terminal, anode is connected to the positive terminal of the battery. Cathode is connected to the negative terminal of the battery. Because anode and cathode are connected in a forward bias condition, majority carriers are moving from N region to P region. Here the majority carriers are electrons. When the electrons are moving from N region to P region, the free electrons, after releasing the energy, they are recombining with the holes in the covalent bonds by releasing the energy in the form of the light. This is how our LED is working. The brightness of the light depends upon our forward bias current. The more forward bias current, the more the brightness of the light. How the forward bias current increases? With the increment of the voltage. We have already discussed diode current ID is equal to Is into e to the power V by neta Vt minus 1. This is the forward bias voltage and current relation. When we are increasing the voltage, the current increases in the exponential direction. So when you are increasing the current, the brightness of the LED is increasing. The brightness of the LED is purely depending upon the forward current. What is the maximum forward current? 30 milliamperes. So the forward current ranges from 5 milliamperes to 30 milliamperes. Here you can see, when we connect this in reverse bias, there is no concept of light emission. In our laboratories, if we use the 1 rupee LEDs, if you reverse bias, automatically they will get damaged. So you should never connect LED in reverse bias. They are designed to operate only in the forward bias. The operating voltage is 1.5 volts to 3.3 volts. Automatically, when you are increasing the LED voltage to 5 volts, it will give the brightness in our laboratories. If you increase the forward voltage to 10 volts, automatically they will get damaged because they are designed to operate until maximum 5 volts. Because their operating voltage is 1.5 volts to 3.3 volts. By this voltage only they will achieve their 13 voltage. Okay, this is the circuit symbol of LED. The arrow represents the which material? P-type material. This vertical bar represents the N-type material. These arrows representing light is being emitted. The light emission is being represented with these arrows. Okay, now you see here. What are the advantages with the LED? Power consumption is less. That's why we have moved from the convention bulb to the LED bulbs. And monochromatic light, whatever the color you want. I need red color. You can use the gallium phosphide material. I need some yellow color, you can use gallium arsenide phosphate. I need orange color, you can use aluminum gallium indium phosphate. I want white color, you can use silicon carbide. Whatever the color of the light you want, based on the PN material you are using, that monochromatic light you are getting, that is the advantage. And they are having the long life. The LED bulbs which you are using in the homes, they will not get damaged easily. Okay, but you may get doubts, sir. You are saying LED, we are operating with the DC voltage, but we are getting supply to the home, AC voltage. In the home LED bulbs, there is a circuit which converts AC to DC, and that converted DC we are giving to our LED. Okay, once again we are revising the concept. What is LED means? Light emitting diode. Okay, in the LED, this is the PN material we are taking. LED is a diode. It is a PN junction diode. LED is a semiconductor material or insulator or conductor? Obviously, it is a semiconductor. It is an intrinsic semiconductor or extrinsic semiconductor, or it is a diode, or it is a transistor? It is a diode. We are taking this diode. Why we have taken two leads? Because diode have how many terminals? Diode has how many terminals? Two terminals. One is anode, second one is, here we have two terminals. This is anode, this is cathode. These two terminals are metallic terminals, or insulators, or semiconductors. Metallic terminals. We are taking the aluminum leads. Why we are taking the reflector? Because after getting the light, we want to emit the light in the entire direction. So we are taking the reflector. Why we are taking the lens? To protect it from the dust and moisture and to give the light in the wide scope. What is the lens color we are taking? Whatever the LED color you are taking, based on that LED color, we design the lens color. Now you tell, LED we can connect in forward bias and reverse bias, or only it should be connected in one bias? What is that? LED should be connected only in forward bias. If we connected in the forward bias, anode should be connected to positive terminal of the battery. Cathode should be connected to? How can we know what is the anode terminal and what is cathode terminal? In the LED, the long terminal represents anode. The short terminal represents cathode. When we forward bias the LED, the majority carriers are moving from N to P. What are the majority carriers in N type? Electrons. When majority carriers are moving from N to P region, here the majority carriers electrons are free electrons. They are in the interatomic gaps. They are recombining with the holes by releasing in the energy in the form of light. Okay? This concept is applicable to all semiconductors, only specific semiconductors we have to use. Specific semiconductors we have to use. This is not applicable to all semiconductors. Only applicable to gallium arsenide, gallium phosphate, gallium nitrate, silicon carbide, and gallium arsenide phosphate, like that. Compound semiconductors. So here, what is the minimum cut-in voltage in the LEDs we have observed compared to ordinary silicon and germanium? What is the cut-in voltage for silicon diode? If you want the more brightness, then you have to give the more supply. When we are increasing the supply, automatically the current increases non-linearly in the exponential direction. The brightness of the LED depends upon the forward current. We have discussed already different color LEDs. White and ultraviolet, infrared, and these colors. Depending upon requirement, we can use these LEDs for our purpose.